So 1.2b, and we're continuing on with functions. We're on graphs of functions. Graphs of functions, it's pretty easy because we do it just the way we graph equations. So example 5, we're given f of x equals x squared minus 5. Okay, so what we're going to do is we're going to come up with that, and we're going to make a chart just like we did with our xy. Okay, so we can pick any number we want for x. Alright, so we put a 0 in there. So when x is 0, what's 5? What's f of x? Negative 5. When x is 2, f of x is 2 squared, 4 minus 5, negative 1. When x is negative 3 squared is 9 minus 5 is 4. So then I just, I'm going to have to, because this is squared, so I know it's not going to be a straight line. It's a quadratic equation. So I'm going to have to get a list of half a dozen numbers there, and then I'm going to draw my graph and then graph each one of those points. 0, negative 5, 2, negative 1, negative 3, 4, and I just go ahead and graph all these numbers, and then I get a graph that looks just like that. Okay, so when I go to the B part of this example, of example 5, I get f of x, and that equals x cubed minus x. And pretty much, just to kind of give you an idea here, the bigger this exponent is, the more numbers you're going to need in order to graph the thing. So we've got, again, x and f of x. And again, we'll learn a faster way to do this later. But I just want to kind of give you an idea of how to do this. So 0. This ends up being 0 cubed minus 0, which is 0. 1. 1 cubed minus 1, which equals 0. 2. 2 cubed minus 2 is 6. Minus 2. Minus 2, the quantity cubed, minus 2 would be negative 8, negative 10. Okay, so you're doing all these problems and you're going to end up with a graph because of the cube that's going to look like this. That's why you need a whole bunch of points here, because this graph kind of goes all over the place. Okay, but one of the things that you'll find out as you get going in math is there's a handy dandy table clear in the back of your book, in the last on the cover, called the Library of Functions. And it will tell you what the graph will kind of look like depending on the equation. So what we just did is a cubing function. First column, third one down. See where it says cubing function? It looks very similar to what I just put on there. And we did, before that, a quadratic function. And if you look in the middle, second row, second and third column, there's two different quadratic functions. One opens up, one opens down. Okay, and that's what the one we did just prior to that. Now we're going to look at a square root function. If you look at the fourth column over, second row down, there's a square root function. So that is going to be, hopefully, what this is going to look like when we do a square root function, because C says f of x equals the square root of x plus 4. So then we do an x, we do an f of x, line, and we put 0 in, and we get 2. We put, let's see, what else can we do? We put in a negative 2, and we get the square root of 2. We put in a 4, and we get square root of 8. I put in a 12, and I get the square root of 16, which is 4. So let's real quickly just give a simple graph here. 0, 2, negative 2 square root of 2, 4 square root of 8, and a 12, 4. So we get a graph that looks like that. Okay, and notice this graph will never go down here, because we cannot have a y value. One of these numbers here cannot be negative, because if they are, then we have the square root of a negative number there, and we're not ready for that yet. So anyway, that's example 5C. Now let's go down to 6. And it says, for the function f of x equals x squared minus 5, it says use the graph to find each of the following function values. So it wants to find f of 3. Now if you look at that graph on the left-hand side of the page, what we're going to do is we're going to look at 3. 3 is the x value, right? So I'm going to go over 3 and then go up to where I get on the line. So when x is 3, y is 4. So when x is 3, y is 4. And notice when you put 3 times 3 is 9 minus 5, you get 4. But just looking at the graph, you can tell that. What happens when f is negative 2? And I guarantee some of these will be on the test, so just saying. That's my x value. So I'm going to go over negative 2, and then I'm going to figure out where I'm at as far as the line goes when I'm at f is negative 2. And notice when y is negative 2, our y value is right there at negative 1. Okay? So it's just being able to recognize on a graph, if you know where x is and they give you the graph, where is the y value? So let's just keep going here. What happens when f is 0? So, I'm sorry, not f is 0, but our f of x is 0. Our x is 0. That means we go left or right, nothing, and then we just go straight down to where the graph is, and it's negative 5. What happens if f is, let's say it's 2? Well, if x is 2, then we come over 2, and to get to the graph, we had to go down, looks like about 1. Okay, so that's what we're doing for those examples. All right, one more thing to determine whether or not we have a function is called the vertical line test. And so hopefully you remember going over this in the past math classes you've had. But for the most part, the vertical line test is a real easy way. It's when you're given a graph and you have to determine whether or not it's a function. Every function, okay, there's a graph. Every function you can take a vertical line and draw through the graph. If any of these vertical lines that we draw could possibly intersect this graph at more than one point, then it is not a function. So that makes it easy. So when I look at a graph that kind of goes like this, and I start drawing vertical lines, yeah, those only go through one point, so it looks pretty good, but then I get right here and it goes through 3. Here, here, and here. So that means the entire thing is not a function. So if you look at the examples, example 7, notice that A is a function, B is not, C is not, because I've got a graph that looks like that, and I can obviously draw a vertical line and hit both of those. Now later on we'll do a horizontal line test to make other determinations. D is not a function. E looks like it is. And F is kind of a goofy one. Those are called piecewise functions. And if you look at F, it is a function because you cannot draw a vertical line through that and intersect something else. It may look like you can because I've got this here, and then I've got this here that goes like that. So what happens when I draw a vertical line? Right through here. Alright, let me explain something about this particular function. The closed circle here means that this number, let's call it -2, it means that this graph here includes -2 and then includes all these numbers here. Okay, -2 is part of the graph. Down here, all of these numbers are included, but because this is an open circle, it says it starts at -2, but it does not include -2. Okay, that's why it's an open circle. So even though this graph looks like it hits that and hits that, it is not hitting this because there is no point at -2. The open circle means it includes all points to the left of -2, but not -2 itself. So it hits -2 here, but doesn't hit it here. All right, so it is a function, and we'll get into what are called piecewise functions later. So this next section is finding domains of functions. I'm going to kind of put a little bit of a stop here to explain something. I think I drew this for Algebra 2. Alright, this is a function box. And the way this works is, let's say that we have an equation in here. Okay, so f of x equals. Alright, we put numbers in here and it's going to spit numbers out. And when we put numbers in there, it's going to use that function in order to solve. So if I put a 2 in here, it's going to kick out a 5. If I put a 3 in here, it's going to kick out a 6. If I put an 8 in here, it's going to kick out an 11. Okay? So given that it's a function, it's going to spit out an answer. Okay? These are the domains. Those are the x values I'm putting in. These are the ranges or the y values or the f of x's that are coming out. Okay, so the domain is the set of inputs. So these numbers here we're going to put in, and the range is the set of outputs that are coming out of the function machine. Okay, so there's my function machine for example 8. So the function that they're giving us is f of x equals 1 over x minus 3. So what we're doing, it says find the indicated function values and determine whether the given values are in the domain of the function. Meaning, is the answer possible? If the answer is not possible, then they are not in the domain. So for instance, let's use f of 1. That equals, so I'm going to take a 1 and I'm going to put it in here. We're going to see what it kicks out. 1 over 1 minus 3, which equals 1 over -2 or -1/2. So when I put 1 in, I get -1/2. Okay, that works. So it ends up being just fine. And f of 1 is defined, and 1 is in the domain of f. Okay, so 1 works. 1 is in the domain. It's a number that will possibly work or will work. All right, let's put in f of 3. So I'm going to take a 3, dump it in the function machine, and see what it kicks out. 1 over 3 minus 3 equals 1 over 0, which is undefined, right? So when I put in a 3, it kicks out a number that's not defined. That being the case, the number 3 is not in the domain of f. It is not a possible number that I can put in the function machine because it gives me an undefined number. It gives me something that doesn't exist. So that's just important to remember that some numbers you put in the function machine, if they spit out an undefined number, then they're not in the domain. Okay, they're not possible numbers that are going to work with what you're doing with these problems. All right, so if we look at B, we've got square root of x plus 5. That's what my g of x is. All right, now notice, before I had an f of x, now I have a g of x. This number here, or letter here, doesn't matter. Sometimes they'll use a g, sometimes an 8, sometimes an f, sometimes a y. I mean, or it just depends. It doesn't really matter. It's just to differentiate that this problem is dealing with a different function. So that's our function. And before I go on, we're going to stop this video and continue with this one in 1.2c.